Okay, let's move on to section 2.2. We take a look at the logarithmic function and also the graph of the logarithmic function. Okay. And logarithmic function are the inverse function of exponential function. Exponential function with the same base. We'll look into that in detail in a second. So in this section, we will recognize and evaluate logarithmic functions. And we're going to graph logarithmic functions. We can recognize, evaluate, and graph natural logarithmic functions. So we're going to focus on three main objectives. Logarithmic function f of x equal to log x, right? Or f of x equal to ln of x. So we're going to take a look at one of them first. Every function of form f of x equal ax passes horizontal line test and therefore must have an inverse function. So we look at a to the x. Something like that. This is f of x equal to a to the x. This horizontal line test indicates it's one-to-one relationship. So once you pass the horizontal line test, then it has an inverse function. An inverse function is what we call a logarithmic function with base a. So it's the same base. Base should be the same. So our definition of a logarithmic function with base a, when x is greater than 0, a is greater than 0, y value equal log ax, even only if x equal to a to the y. So meaning logarithm could be converted back to the exponent. So taking the base raised to the y power, that becomes x. And this f of x equal log ax, whereas log base a of x. Log base a of x. So logarithm function with the base a. And a could be any number greater than 0. A cannot be 1. Alright, so now we know these two are inverse functions, logarithm function and exponential function. So they can go back and forth. So if you have a logarithm function, you can easily convert it back to the exponent. If you have an exponent, you can convert it back to the logarithm function because they are equivalent. So that being said, so 2 equal log 3, 9 is equivalent to 3 squared equal to 9. So do base raised to the power 2 equal to 9. That's true, right? Because 9 equal to 9. And here you can turn this 5 to the cube equal 125 as log 525 equal to 3. Base is 5. The y value is 125. So log 125 equal to 3. So converting the logarithm to exponent to logarithm. Now when we evaluating logarithms, remember that logarithm is an exponent. That means you can easily convert it back to exponent and solve for the unknown variable x. So for example, let's say we have log 2 equal to 3. And that's the same thing as 2 cubed equal to 8. Going back to the exponent. If you look at this, let's say we have something like log 2x equal to 3. Then we know that 2 to the cube equal to x, right? So that means a equal to x equal to 8. If you have unknown in the logarithm, you can also convert it back to exponent and solve for the unknown. All right, now let's take a look at the following examples. Right? Part A, f of x equal log base 2 of x, x equal 32. And we're going to solve it, right? So when x equal to 32, replace x here with 32. And we can use another property. So log 32 is 2 to the 5th. When the logarithm and exponents have the same base, they cancel each other. This property comes from this log ax equal to x. So they offset each other because they are inverse function of each other. Cancel that, get 5. You can also look at it as this. Let's say we don't know what that number is, but assuming it's variable x. So 2 to the x equals 32. And we know 2 to the x equals 2 to the 5th. That's why x equals 5. And that's why the answer is 5. And second one, copy f of x equal log base 3 of x. Now x value equal to 1. So log 3, 1. Okay, log 3, 1. And this is log 3, 1 equal 3 to the 0 power. So the answer here should be 0. Another way of looking at it is log 3 equal to, assuming this is equal to x, and we try to solve for x. Another way of looking at it is log 3, 1 equal to x. Right, so now we do 3 to the x power equal to 1. And we know that x value must be 0 for this equation to be true. And that's how we solve it using the exponent. Right, so either way is good. Part C, f of 2. So we have f of x equal log base 4 of x, log 2, when x becomes 2. F 2 equal to radical of 4, square root of 4. Square root of 4 is 4 raised to the half power. And again, logarithm with base 4, exponent with base 4, they offset each other, so end up with half. Another way of looking at this is setting log 2 equal to x, and then we get a 4 raised to x power equal to 2. We know that 4 to the x, 2 is the radical 4. So 4 to the x is equal to 4 to the half. Now x must be equal to half. There's different ways of solving this. And part E, f of x equal to log base 10 of x. Now x value here equal to 1 over 100. So replace x with 1 over 100, we get this log 10. 1 over 100. 1 over 100 is 1 over 10 to the second. And flip the exponent to the top, we end up with 10 to the second. Now the logarithm and exponent with the same base, they offset each other, so we end up with -2. So that's how you simplify this logarithm expression, solve for the unknown numbers here. So logarithm function with base 10 is called a common logarithm function. Denoted log 10 is denoted by log 10 or simply by log, log. Most calculators, the function is denoted by log, right? Log. You can find it on your calculator directly. Following properties apply to the logarithm function in the base A. So log A1 equal to 0 because A to the 0 power equal to 1. Log AA equal to 1 because A to the first equal to 8. Log AA raised to x equal to x because logarithm exponents are inverse function of each other, so they cancel each other, we end up with x. Exponent with base A raised to log ax. Exponent and the logarithm with the same base, they cancel each other, we end up with x. So this is what we call the inverse of these. And for log ax equal log ay, and x equal to y. This is what we call the one-to-one property. Alright, so now let's look into the graphs of logarithmic functions. And first one, we look at y equal log ax. So we know that this is the inverse. We can turn it back into the exponent because a to the y equal to x. And logarithm exponents with the same base are symmetrical with respect to the line y equal to x. y equal to x is called identity function. So logarithm y equal log ax and exponent y equal e to the x for the mirror image based on y equal to x. So very important feature about the inverse functions. Now, in the same coordinate, sketch a graph of each function f of x equal 2 to the x, g of x equal log 2x. So we start with f of x equal 2 to the x. All right, so we already talked about this earlier from the slide. So come up with a 5-order pair, start with -2, -1, 0, 1, 2. And from here, we can find the y values. So f of -2 equal to 2 raised to -2nd power. And this is actually the same as 1 over 2 to the second, which is quarter is 0.25. And f of -1 is 2 to the first power. So it's 1 over 2 to the first is half. As you can see, it's doubling right now. Right? When x value is increased by 1 unit and y value is doubling because the base is 2. And f of 0 is 2 to the 0, that's 1. The 1 is 2 to the 1, that's 2. 2 is 2 to the second, it's 4. So we have 5-order pairs so that we can sketch that. Next thing, so we get all these 5-order pairs, mark those numbers, and then we're also gonna come up with the g of x, log 2x. G of x equals log 2x. Now, similarly, we can come up with 5-order pairs. The way how we're picking the x values, I'm going to show you how to do this. So the first x value, we're going to pick 2 using the base to the second power. And we know that's a quarter, right? And g of x, g of 2 to the second is log 2 to the second. Now we're done with base 2, exponent base 2, they offset each other, so end up with -2. We go back to the previous, you see quarter, -2, right? So the xy values actually just switch. We switch xy values, get a logarithm function. Secondly, using 2 to the 1 power, so this is half. So g of 2 to the first power is log 2 to the first, so this is -1. Again, it's the inverse of the other exponential function. So g of third one is 2 to the 0, so that's 1. 2 to the 0 is log 2 to the 0, that's 0. And then g of 2 to the first equal to 2, so g of 2 to the first is log 2 to the first, that's 1. And the last order pair is 2 to the second, that's equal to 4. Of 2 to the second is log 2 to the second. Again, that becomes 2. And we get all these order pairs, so then we can sketch this. We start with the exponential function first. For the exponential function, 5-order pairs, when x equal to -2, y value is a quarter. Quarter is right here. And then when x equal to -1, and y value is half. 0, 1, 1, 2, 2, 4. And connect those. We did it from the last section. Extending in both directions together. Right? For the exponential function f of x equal to 2 to the x. Now we're going to sketch the logarithm function. Alright, so the first order pair is quarter and -2. 2 is here. Quarter, this is half, that's a quarter here. And 2. And then half equals 1. And 1, 0, it's right here. And then 2, 1, that's here. And 4, 2. And then we're gonna connect those 5 order pairs extending in both directions. And as you can see, these two curves, smooth curve is from a mirror image based on y equal to x. This is logarithm g of x equal to log 2x. So they form a mirror image based on y equal to x. Alright, so that's how you sketch the graph step by step. And then you always picking the number based on the base here. You always give us the sophisticated graph. This is just something, summarizing what we have here. So f of x equal to 2 to the x, g of x equal to log 2 over x. They form a mirror image based on y equal to x. And then the important thing is domain of the exponential function is the range for a logarithmic function. It's the same thing as range. Domain is x. X becomes y. The range of the logarithmic function. And then the range has y value for the exponential function. It's a domain for a logarithmic function. So basically, it's x becomes y value becomes x value. And if you look at log with base 10, right? F of x equal log base 10, and we can easily sketch the graph as well. F of x equal to log. Here, there's no number, but before it's 10. And we actually can come up with 5 other pairs. First one is when x equal to 10 to the negative second, and this is 1 over 100. And the y value here, f of 1 over 100, we did it earlier, it's log 10 to the negative second. We simplify that becomes -2. Same thing here, 10 to the negative 1 is 1 over 10, give us -1. So this power becomes y value. 10 to 0 power, that's 1. That's 0. Right? 10 to the first is 10, give us 1. 10 to the second, that's 100, that gives 2. As you can see, 10, 1, right? So 10, 1, 100, 2. We get a 1, 0 right here. And then 1 over 10 is equal to 1. This is equal to 10. And you connect those points and get a logarithm function in the base 10. And let's summarize the basic characteristics of the logarithmic function graph. First of all, log with the base a when a is greater than 1, The domain is from 0 to infinity. So this is the domain from 0 to infinity, not including 0. The range is from negative infinity to positive infinity. And then x-intercept is 1, 0. So 1, 0. From left to right, it's increasing. It is 1 to 1, therefore has an inverse function. And the inverse function, we know that it's exponential function with base a. And y-axis is the vertical asymptote. If you look at this y-axis here, that's vertical asymptote. So the graph of the logarithm function approaches y-axis, but never passes through that. And it's continuous, meaning it's a smooth curve. There's no jump, no break, no hole there. It's a smooth, continuous curve. And it's a reflection of the graph of y equal ax about the line y equal x. And the basic characteristics of the graph f of x or ax shown below, and these two are inverse of each other. For f of x equal to a to the x, exponent of the base a, domain is all real numbers, range is from 0 to infinity, so the domain of the logarithm becomes the range of the exponents. The range of the logarithm becomes the domain of the exponent. So they are inverse of each other. Okay. So y-intercept here 0, 1. X-axis is horizontal asymptote. As ax approaches 0, then x approaches infinity. Now let's take a look at natural logarithm functions. Right? So for example, like y equal to e to the x. We're talking about e here is possibly 2.718. Now we'll see f of x equal to e to the x is 1-to-1 function. It has an inverse function. Inverse function is f of x equal to log ln of x. Or you can say log the base e of x. Inverse function is called natural logarithmic function. It's denoted by the special symbol ln of x. Whereas natural logarithm of x, ln of x. Natural logarithmic function, the function defined by f of x or log e x equal to ln of x. Here x is greater than 0. It's called natural logarithmic function. And basically, natural logarithmic function and the natural exponential function f of x equal to log dx or ln of x, and the exponential function f of x equal to e to the x, they are inverse of each other, so they form a mirror image based on the y equal to x. Y equal to x is what we call a symmetry line. So we can easily turn y equal to ln of x as exponent. So we do y equal to log dx b raised to the y power, that's equal to x. So they are equivalent of each other. Because they are inverse, f of x equal to e to the x, and g of x equal to ln of x, inverse function of each other, the graphs are reflection of each other based on the line y equal to x. Next thing is I'm going to show you how to sketch the graph of g of x equal to ln of x. G of x ln of x. So similarly, we'll get order pairs. Five order pairs. Since this is log with base e, so we're gonna pick e to the second power. This is 1 over e squared. So when we have 1 over e squared, then log e, e to the second power equal to 2. So the y value equal to 3 of that is equal to 2. So e to the first power, which is 1 over e to the first 1 over e, and g of let me just quickly redo this. So let me share the detail one more time. G of e to the second equal to log e to the second. So now logarithm base e, exponent with base e, they offset each other. So So similarly, g of e to the first is log e to the first. Offset each other, and so end up with negative 1. So here is negative 1. And then e to the 0, that's 1. So g of e to the 0 equal to log e to the 0. So they, again, logarithm and exponent of the same base offset each other, end up with 0. Exponent g e to the first is log e to the first, that's equal to 1. E to the first is e. G of e squared is log e squared. Offset each other, we get 3. So e to the second is 2. Okay. So as you can see, when you sketch a graph here, 1 over e corresponds to negative 1. So this is one point here. 1, 0, it's here. 1, 0. And then e1, right? So those 3 points connect them, you get a logarithm function. We can plot a little bit more here, but once we know the curve, the shape of the curve, then we will be able to do that. And f of x e to the x symmetrical with respect to y equal to x. So we also form a mirror image based on the identity function. Okay. And that's how you graph the logarithm with base e. And now let's just work it out, how they simplify all these concrete numbers here, log 10. 1,000, we know that is 10 times 10 times 10, which is 10 to the third. So log 10 base 10, 10 to the third, which is equal to 3. So log 3, 81, and 81 equal to 9 times 9. 9 times 9, we can further expand it 3 times 3 times 3 times 3. Log 3, 3 to the 4th equal to 4. And log 5, 125 is log 5, 5 to the third. 125 over 5 to the third is equal to 3. And then the example 4, all those, you got to use a calculator. So I'm going to show you how to do this in Excel on the calculator. So ln of 20.5. You open Excel, equal sign here for ln of 20.5. So get a result. So the answer is 3.02. This is approximately equal to 3.02. Okay, let's try the other one. The other one is ln of 0.35. You can also find it from the calculator. So ln of equal sign ln of 0.35. So this is equal to negative 1.05. Negative 1.05. That's how you evaluate these logarithms in a calculator or Excel. So let's quickly summarize 4 properties about logarithm. The first one is ln of 1 equal to 0 because ln of 1 is log e1, right? Equal to 0, then you can turn it back into the exponent, e to the 0 becomes 1. ln of e equal to 1 because log e equal to 1, that means e to the first equal to e. That's always true. And that's the inverse property, ln of e to the x equal to x, e raised to ln of x equal to x. So because they are inverse of each other, so cancel each other, we end up with x. We have a logarithm equation with respect to base e. Ln of x equal ln of y, that means x must be equal to y. And then we call this one-to-one property. And in the real calculation, sometimes we need to use some of these properties. So it will be handy when we can try to understand this. Okay, that's pretty much everything on section